In today's video, we're going to learn about static load, failure, and the strength of materials. Now, static loading is a condition when forces or loads are applied at a very slow rate in a structure or material. Essentially, we are applying loads such that the effect of time and the effect of inertia within our structure and impacting structure are insignificant. If we were to say plot force versus time, we have a very low loading rate, and then eventually we will reach our static load point, which is constant with respect to time. Now, failure can mean many different things. Failure can mean that a part, once it's reached its static load, separates into two or more pieces. It could mean that a part permanently or plastically distorts, ruining its shape. It could also mean that a part just becomes less reliable, so it's inconsistent in its performance, or that its function is compromised in whatever reason. As an engineer or as a designer of a part or a structure, failure can mean any or all of these possibilities. Now, in this chapter and in our book, we're going to focus on failure, which is related to fracture. And that is where our static load is increased until it reaches a critical value, the break force, at which our part separates into two or more pieces. That can be illustrated as follows, where we have the force on the y-axis, time on the x-axis, and we slowly increase our load until we reach the point that force at break occurs, right? Where the force is equal to the force at break. Now, a key thing to note when we're dealing in the units of force is that that force is dependent on the loading condition. Force can be a vector. Forces at a distance can create moments that cause bending. But also, force is a unit in newtons. Moments are units in newtons times meters. And they have no relationship to the actual geometry that we're testing. That means for every different type of part that you make, it's going to break at a different force that's applied to it. It's not going to have the same force at break, this part or that part. And so, rather than using force at break as a property to try to design any part, a better failure parameter is what we call the ultimate tensile strength. This is the maximum engineering stress that a material can sustain before failure occurs. It's calculated in the units of stress, where the ultimate tensile strength is equal to the force at break divided by the cross-sectional area over which that break occurred. So the area where it broke at. Now, the combination of stress, which we can calculate from our geometry, and the ultimate tensile strength, which is a property of whatever particular material we choose, that combination allows us to evaluate failure in a wide variety of geometries and to be able to select which material can meet the design requirements for our geometry. And so the inequality stress, if stress is greater than or equal to the ultimate tensile strength, then failure arise, this criterion for failure. Now, the reality in parts, in real parts, complex parts, is that the stress distribution is not uniform. In fact, in previous videos, we learned that for even a simple beam, if it's subjected to a couple of different forces and moments, it has a state of stress where stress is a tensor that includes 6 different values of stress that are calculated from the geometry and normal stresses and shear stresses. So for real parts, stress isn't even that simple, right? It's not just one value, but it's a tensor of values, right? Now, in terms of the ultimate tensile strength, the material property, how do we arrive at it? Well, the first thing we do is we'll get a sample of our material and we'll machine it into what's called a tensile test bar. And this bar we will load with force with a quasi-static loading condition, very slowly increasing the force. And when we do, we record the force that we've applied to it, and we record the change in length of the gauge length of the sample, which then allows us to calculate the strain. And at a certain point at the critical force, our bar will fail, and then we'll process that force and displacement data into a stress strain curve. Now, depending on our material, there are two types of behaviors that we see. We can see ductile failure, where there's a lot of plastic deformation before our part fails. And then there are materials that have brittle behavior, where they are primarily elastic and then they fracture very sharply and unexpectedly. In both cases, the ultimate tensile strength of the material, here this is called SU, here it's called SUT, is the largest engineering stress observed in this stress strain curve. It is the maximum stress that a material can sustain before it starts to deteriorate. Now, with ductile materials, once we reach the UTS, beyond that point, our part starts to neck down. So the cross-sectional area starts to decrease. The maximum load stress we can sustain decreases, and then we get fracture. Generally, when we're designing a part, if we get past this point, it's failed. The part is done, right? But because of that additional ductility, ductile materials are a little bit, we have at least some awareness that our part will fail. We have awareness that our part has exhausted itself. It has permanent deformation in its shape. This doesn't look right. We need to replace a part. While for brittle materials, because there is little to no plastic deformation, the instant that we reach the UTS, we have an instantaneous fracture that occurs in our part, and it's not good, right? So, whenever possible, and when we're designing a structure, we want to try to use ductile materials, because ductile materials will tell us through the change in shape, the plastic deformation that they have, that they are getting closer to their end of life.